Thank you very much for joining today's online event about HSR and PRP in digital substations. I'm here today with Alicia Alonso from Relyum, and my name is Justina from Velotech. Before we start with the agenda, please note that you can ask questions at any time. We'll go through the presentation, which will take around 30 minutes, and then we'll have enough time to answer all of your questions. Regarding the agenda, I'll start with the introduction to HSR and PRP, and then Alicia will go a little bit deeper into the details. Also talk a little bit about PTP, so Precision Time Protocol, and sampled values processing for real-time applications. At the end, I will summarize and talk a little bit how you use HSR and PRP in substation servers, including virtualization for different applications. Let's talk about PRP. PRP is a network protocol. It's a parallel redundancy protocol. This means that within a network, we can have a redundancy to avoid packet loss or loss of communication. PRP is a protocol that is sending the data into two networks at the same time. On the one hand, we have a so-called SAN, which is a single attached node. This could be any device connected with one Ethernet cable and one line to a network. Connecting to a red box, which is a redundancy box, offering this device to take part in the PRP network. And then the data is sent over two different networks with standard Ethernet switches to a so-called DAN, which is a dual attached node. A dual attached node is a device that has two Ethernet ports at the same time, and the packages are received over LAN A and LAN B, and the first packet that is arriving is accepted, and the second one is discarded. So you can use PRP in multiple network topologies within substations. It's a protocol that is also part of the IEC 61850 standard family. And it allows you to have zero delay recovery time and zero frame loss, so for high reliable networks. Very important, it's a switching protocol, so it's layer 2, so you don't need any routing or software stack or anything within your application to run PRP. Now let's talk about HSR. As you can see in the picture on the right side, HSR is also working with single attached nodes and dual attached nodes. So from the principle, it offers the same redundancy as PRP. But with HSR, we have a ring network. This means that we don't need additional switches or LANs. Every DAN is connected to the next DAN, and at the end over a red box, which means redundancy box, to the standard network. In HSR, the packages are sent from the origin to the red box, and then the packages are sent directly in two directions of the ring, so that every package is sent twice. And at the receiver, the first package is accepted and the second one is discarded. So you have ring technology and don't need additional switches to run it. Same as PRP, HSR is also defined in the IEC 61850 standard family and made for substations and especially digital substations. And which is also important, is it's also a layer 2 protocol. So also for HSR, you don't need any additional software stack for your application. Okay, perfect. This was the first short introduction. And now I hand over to Alicia. Alicia, please go a little bit detailed in HSR.
Thank you. This slide shows how multicast traffic is sent through an HSR ring. This is a very interesting use case because with multicast traffic, all the nodes in the network are the destination nodes. So here in this drawing, you can see how the duplicate card is not discarded until it reaches the last node, which is in that case the source node, the source node. So here also you can see the two elements that were mentioned by Josh, the red boxes that connect the single attached nodes to the ring, and also the dual attached nodes which implement which have the functionality of the red box functionality embedded in the node. Okay. So next, yeah. So after reviewing these first initial concepts about PRP and HSR, let's see which are the most suitable applications for using PRP and using HSR. I will start with PRP, and for a better understanding of this, which are the most suitable applications, I will review which are the pros and the cons of this technology. So starting with PRP, the PRP technology or topology is based on implementing two standard networks. These, I said standard networks. That means that you can use standard switches available in the market for implementing PRP. So any switch compatible with regular Ethernet, any switch that already implements or includes layer 2 features like, for example, VLAN configuration, frame rate limiting. So all these mechanisms that are available in regular or standard switches can be also used in PRP for doing traffic shaping. And this is a very interesting feature when you can have in the network very high loads of traffic and you want to prevent from congestion. So on one side, you have the traffic shaping feature that is available in PRP, and also the fact that it's completely compatible with regular Ethernet. So you can connect regular Ethernet elements to a PRP network. But opposite to that pros, you have an important constraint with PRP is that you have to implement a two full networks with extra switches to do the redundancy. So you have to invest in purchasing these switches that I mentioned, but not only an initial investment for the devices, but also for the engineering of the configuration of those devices, which is many times complex and require advanced engineering skills. And also, after the first implementation, you need to take into account the maintenance of those devices. So it has important benefits, but it has an extra cost compared to HSR. So attending to these pros and cons, which are the most suitable applications? Well, the first case is when you already have some switches, you are starting from an existing network, so you have switches, and it's easier to implement the redundant network from that point. So the extra cost of a PRP implementation is reduced with this initial investment. Also, it's an interesting technology for redundancy when you are working with big systems, like for example, transmission substations, where you have a large number of IDs and with a high throughput or high traffic injected into the network. So in that case, it might be very interesting to use some layer 2 mechanisms to do some traffic shaping. For example, for configuring VLANs, for configuring different paths and different segments in the network to define which traffic is going to be sent in this part of the network. And also, it's a very common protocol used for a station bus in a substation. The reason for that is normally in the station bus is self-contained in the control house. All the elements that are connected to the network are in this space, in this location, in the control house. So there are no long distances between them. And with only two switches, with two standard switches, it's very easy to implement this seamless redundancy. So it's a very efficient solution and cost affordable in terms of investment. Okay. So now let's switch to HSR, and I will follow the same scheme for talking about this technology. Firstly, the pros of HSR, and opposite to what I mentioned in PRP, in that case, there's no extra equipment needed. So no switches that have to be purchased, no extra engineering that has to be considered when implementing this type of systems. And once the system is running, no maintenance cost for maintaining these extra switches. The reason for that is because the red box themselves, the dual attached nodes, are the switches in the network. So no additional equipment for implementing HSR. Also, it has a very good performance in terms of cost savings in long distance installations, mainly because of the topology that is related with HSR, the ring topology. For example, let's talk about a process bus in a large substation where you have many elements in the switch yard, and all these elements are separated between them for long distances. If you decided to install a PRP network with a star topology, connecting all these elements, for example, to the control house where the switches would be installed, you will need to invest a lot of money in those cabling and wiring to the control house. With an HSR topology, with a ring topology, you obtain important savings in terms of wiring and cabling by interconnecting the IEDs in the switchyard between them. So this is also an important benefit of the topology of HSR for long distance installations. And finally, the third benefit of this technology is that it has a more deterministic behavior. This is important in deterministic applications because you can calculate which would be the latency in the worst case scenario. This latency, the maximum latency of a packet, would be the one that the time that takes one packet to go through all the nodes in the network, because this will be the worst case when you have to send a packet to the node that is just next to you, but instead of using the shortest path, you have to go through the longest one. So these are the main three benefits of HSR, but there's an important constraint with this technology compared to PRP, is that it's a very basic mechanism that is used. All the traffic has to be sent through the two paths of the ring without being able to apply traffic shaping on the network. So even if the red boxes support some layer 2 mechanisms, when using HSR, it's not possible to do this traffic shaping. So in case you have a lot of traffic in the network and you want to do some type of segmentation or configuration, this wouldn't be possible with HSR. So attending to those benefits and constraints, which would be the most suitable applications for this technology? Well, first of all, small substations where you don't have a very high number, for example, of IEDs. So you won't have a very high traffic or amount of traffic in the network, and traffic shaping mechanisms are not really needed for transmitting all this information. Also, a second use case very, very frequent for HSR is the process bus. I explained a little bit in the previous slide the topology of a substation with a switch yard and all the elements separated long distances between them in big substations makes that in process bus HSR is more suitable than PRP. Also, normally sample value transmissions have some deterministic requirements, and HSR has one of these characteristics. It's more deterministic than other Ethernet technologies. And finally, we see that in renewable plants like wind farms, in small power plants, HSR is becoming very, very frequent. The reason for that is because normally these plants are self-contained, they are independent. So it's very easy to manage the traffic that is sent in the network with an HSR ring. Also, for example, in the case of wind farms, you have all the elements separated long distances between them. So also a ring topology is a very good choice for implementing a network in those kind of systems. So after reviewing the main concepts of the protocols and which are the most stable applications, I will try to focus on some specific particularity of PRP. HSR is a very demanding protocol, so normally all the implementations are based on hardware platform. In the case of PRP, you can find two types of implementations. On one side, you can find software solutions based on a software implementation combined with the regular Ethernet NIC, for example. And on the other side, you can find PRP hardware implementations that are normally based on FPGA technology, on an FPGA platform. So before going forward and seeing which are the advantages of this type of solutions, I will focus on explaining briefly what is an FPGA chip. The characteristic of FPGA chip is that it's a reconfigurable technology. It's known as blank chip. Also, it's known as programmable logic. So as a blank chip, the functionality of this device will depend on the design that is loaded on it. And you can load different designs and it will, the behavior of the chip will vary or change depending on the design that is loaded on it. So this is one of the characteristics of FPGAs. And the second one is that compared to software that it has a sequential operation, FPGA performs as an ASIC. So it's hardware and all the computation is done by hardware. So it's very, very suitable for low latency applications with demanding processing and that only can be implemented by hardware. Another important thing is that in the first times, FPGAs were sold like independent chips. At this moment, FPGA manufacturers have evolved to the concept of system on chip, SoC. So what is a system on chip? It's a chip that includes not only the FPGA, like you can see here in the picture, but also some CPUs, some memories, and other elements that can be complementary to the FPGA for implementing a full application on it. So after reviewing what is an FPGA, let's focus on what does a hardware implementation of PRP mean and which can be the advantages of using this type of solution. Well, basically, if you opt for a hardware implementation on a separate board, you make that PRP will be independent from the host CPU of the main platform. It will be completely decoupled, and it has the benefit that it offloads the CPU for having to do some extra computing or processing, for example, for generating the supervision frames, duplicated, remove duplicated, and so. So it's a great benefit for the CPU because it prevents from overflows in the processing of the main application. The CPU of the host is focused on the main application, then user application, for example, the control of the substation in the SCADA or the control of the performance of the protection. And PRP is implemented separately from that. Also, another benefit is that as PRP is completely independent from the CPU, you can install any operating system on the CPU that it will be compatible with the PRP implementation. So you can have in the CPU Windows operating system, Linux, VxWorks, any virtualization solution or so. It's independent, it's transparent for the PRP implementation. Also, once you are investing in a separate hardware platform for implementing PRP, and normally based on an FPGA, the most common thing is to find that the same platform is in charge of implementing the synchronization of the network or of the device. So it's the CPU, it's offloaded from the PRP computation, but also from the PTP computation. PTP transparent clock is performed in the FPGA of the separate hardware, and PTP software computation is also performed in the CPU that is embedded in the SoC. So all is completely self-contained in the separated platform that runs the PRP implementation. So yes. So these were some benefits that are faced on the side of the CPU of the main platform, but the same benefits we can find in the implementation of PRP itself, in terms of robustness and in terms of high availability. PRP performance won't be affected by any overflow issue in the CPU of the host board. So this is very important because it's a way of guaranteeing robustness in the implementation of PRP. And very important for high traffic applications, only with the hardware implementation, it is possible to reach a full speed operation around, for example, 1000 megabytes per second. With the software implementation of PRP, those throughputs will never be reached. So it won't be possible to make use of the full bandwidth of the network. And this is very important in some cases, in some applications. So this was some benefits regarding the CPU and the performance of both the application in the CPU and the PRP solution. But there are other benefits regarding the FPGA itself. As I explained before, it's a reprogrammable chip. So it's possible to evolve the technology to adapt to the latest version of the standard and to add new features once they are needed in the application. Just by upgrading the chip, it's very easy. You don't need any special tool. It can be reflashed and it can be completely adapted to the new needs of the project. Also, FPGA is a type of technology that is being designed for critical systems. So the end of life of this type of products is around 25 years. And this prevents from obsolescence, very important in sectors like energy sector. And once you have a hardware, separate hardware with these capabilities with an FPGA, you can implement advanced architectures like the one that is shown in this picture, where you see that PCI card with PRP implementation or HSR implementation by hardware can do quad box operation and combine an HSR network with a PRP network. Those kind of complex architectures can be performed with devices that are using a hardware PRP implementation. And finally, once you have the FPGA, you can add other functionalities in the same chip, like, for example, doing wire speed ciphering and deciphering, sample value preprocessing, and any other low latency application that can be implemented in an FPGA chip. So after talking about PRP and HSR, I will talk a little bit about PTP, precise time protocol, which is many times related with the other networking protocols, and you can almost always see them together in substation networks. PTP is a synchronization standard that is defined in the IEEE 1588 standard. This standard defines the main concept of the synchronization, and then you can find profiles for each sector that define how to implement those concepts of the synchronization in each particular sector. So for substation automation, the profile that defines how to implement synchronization is known as power profile. This profile was defined originally in the standard IEEE 37.238. In parallel, the group that was working on the definition of HSR and PRP protocol in the standard 62439 defined the Annex B, one specific annex for explaining how to implement PTP over HSR and PRP networks. And this was known as industrial profile. And later, a few times later, the group that was defined in 61850 took all this information from the previous two documents and added it to the standard with the number -9.3 for defining the power utility profile, which is the most common nowadays in the substation automation systems. So which are the main components of PTP? Well, we can find transparent clock mechanism, which is implemented normally in the switches and which is in charge of calculating the delay that is added by the switch when transmitting the time reference in the network. So what transparent clock does is to correct the reference to taking into account that delay that I mentioned before. Then you have the ordinary clock, which is a mechanism that is used by the slaves, by the end devices connected to the network, for getting the time reference from the network and for synchronizing themselves. The master clock mechanism, which is in charge of getting the time reference from a GPS source and sending the time reference, injecting it into the network. And boundary clock, which is a special mechanism that is used by gateways in the network for managing different clock domains in the network. So now I'm going to make a quick overview of which is the process that has to be followed by the slave for synchronizing itself. First of all, you have the grandmaster, the PTP grandmaster, that normally has a GPS receiver connected to it to get an accurate time reference from that element. With this reference, it generates the PTP supervision frames and it sends it into the network. When this PTP supervision frames goes across one switch, the switch has to calculate the delay that it's introduced by itself and corrects the time reference taking into account this delay. And again, it generates a PTP supervision frame and send it into the network. And you can follow different hops until you reach the destination, one of the slaves that extracts the time reference from the supervision frame and synchronize itself with this time reference. So this slide is just to illustrate how PTP matches so well with HSR and PRP. It's been implemented for many years in many substations, and you can find complex architectures like the one that is shown here, where you have two PRP networks, one with the identifier 1, the second one with ID2, with their LAN A and LAN B. You can have one time reference in one of the PRPs, another time reference in the second one, and you can even connect these PRP networks to an HSR ring. So you will be able to manage the two time domains through red boxes operation, and all these complex architectures are completely defined and explained in the standards that I've mentioned before. So it's a very robust and strong implementation and solution. And now, after talking about the protocols and the concepts and the fundamentals of these technologies, we are going to present some specific products that implement all these technologies that we've been explaining before. We're going to start with this device that is shown in the picture. It's a PCI card that is based on a hardware, an FPGA design. So it can do hardware implementation of PRP. And it benefits from being able to combine in that FPGA different applications that demand low latency calculation. So in that specific case, you have one device, one single device that supports HSR and PRP communications, PTP synchronization, both transparent clock, master clock, and ordinary clock in the same device, and also sample value preprocessing. So we've been talking about HSR, PRP, and PTP before. Now I'm going to explain what does this sample value preprocessing mean. This particular device can implement in the same FPGA and discrete Fourier transform for calculating the magnitude and the phase of the first harmonic of the signal. It can also calculate the root mean square of the wave of the electric signal that is received in the sample value data, and it can implement sample value decimation for example, to post processing in terms of quality and so when the number of sample values that are needed is much lower than the normal one, and it can do all this computation for up to 10 simultaneous sample value streams in the network. In parallel, it can send in real time all the results of these computations, so all these 10 per 3 calculations to the host computer that will be in charge to do post-processing, like for example, fault detection and other electric algorithms application in the system. So which are the benefits of using that type of platforms? No? The main benefits is that in a context of digitization, where you have large amount of information and data available in the network, that leads to do some distributed computation and to define new centralized application, being able to offload to the CPU of all these computations. It's a very interesting way of approaching the new applications that you can define in these new systems. I was talking about centralized applications. Suppose an example, a central protection, which is something that is being considered in some utilities. We've been working closely to some companies that are working on R&D projects related with this new concept. You have to manage HSR and PRP communications, PTP synchronization, sample value description, and those preprocessing that is needed for doing the detection of the fault. Well, you can offload the CPU, you can let that the board itself implements the first steps of the processing, and then the CPU can focus on the main application, which will be the protection application itself. So when you're talking or you are working in the conventional system where you have one protection that takes charge to a small part of the substation, this protection has to manage only maybe 2, 3, 4 sample value streams. But when you're talking about a central protection, the number of streams that have to be managed by a protection or by a device increases up to 10. So in that case, a standard computer won't be able to manage such a big amount of data. By using these combined solutions, central protection can be implemented without having to invest in a very important or high resources computer. And this can be extended to other central applications like protection and control, central telecontrol, monitoring, quality, and so. And is very aligned with the new concept of virtualization, where you have a very powerful central computer that is in charge to implementing different applications related to the electric world.
Okay.
Thank you.
Thank you, Alicia. Now I'm talking a little bit how to use HSR and PRP and also PTP and sample value processing within a card and then use it in virtualization in a substation server. The idea behind is that you're merging OT and IT capabilities, because on the one hand, you have IT-driven trend that separates hardware and software and use virtualization or applications on a server, including HMI, substation gateway, and so on in the station bus, usually connected over PRP to the lower process bus and so on. And there you usually have hardware or software implementations, and we have seen the advantages of the hardware implementations, so you can directly use it. Another advantage is that you can not only use one card inside of one of those servers, but up to 4. So you can have a lot of different networks connected, also possible and available for larger substations. In addition to that, the server itself can really concentrate on the applications, on the virtualization tasks. If you're running gateway, HMI, and so on in parallel, or if you're moving down to protection and control for the process bus, you don't need like 24 core servers, but can do everything with lower servers in a fanless operation. In addition to that, the system offers security with TPM 2.0 module integrated for modern administration and identification of the devices. With the OT capabilities of HSR and PRP, you also have directly the PTP support, which can direct also the time much more accurate to other systems, for example, Windows and Linux. And the whole solution, which is very important, is working at minus and then plus temperatures from minus 40 to plus 70, 75 degrees, and is fully IEC 61850-3 certified for EMC, temperature, shock, and vibration, and so on. So if you put HSR and PRP cards into a substation server, as we do in many projects, the server itself becomes a dual attached node for HSR, mainly in the process bus, or a dual attached node for PRP, mainly in the station bus. And as Alicia mentioned before, you have seamless HSR and PRP and PTP support and support inside of the device without your software needs to take care of this, needs to you don't have any need for additional processing power of the host CPU, which is working on your HMI gateway and engineering workstation applications. The whole solution is compatible with standard Windows operating systems, Linux operating systems. The reason behind this, for the operating system itself, the card or the PRP or HSR network just looks like a standard Ethernet port. So you don't need to have any modification of your application. In addition to that, you have also more networking and monitoring possibilities, including SNMP, system log, and so on, so that your system becomes really IT ready with this type of solution. Also, your network becomes IT ready. Now we are jumping to the question and answers. I've seen that some questions came in already. Please ask more questions at any time, and we try to answer them all. Let me start with the first one. There's a question for Alicia. Can we implement HSR PRP connection between substations?
Directly connection between substations, HSR and PRP.
Yes, so connecting, I guess, connecting two substations, yeah.
It's not very frequent because normally the type of technologies that are used between substations are different. Sometimes it's radio or other technologies, but we've been working on some projects where our partners were using HSR ring for interconnecting substations. So yes, it's possible to use them. It's not the most common because normally the way the engineering of the substation is done differently, and there are other technologies that are maybe adapted to long distances that are more suitable for those type of one connections. But we've been some customers that even they have implemented a type of HSR redundancy over wireless links. So yes, it's possible to apply redundancy based on HSR and PRP on one links.
Okay, thank you. Next one, can PTP and NTP coexist in the same network?
Yes, and it's something that can happen frequently. You may have some devices that use NTP synchronization and that are not able to support PTP. Maybe it's a configuration computer or so that doesn't require such a precise synchronization. And then you have the merging units and other critical elements that support PTP. Normally, the only thing is that you need to have NTP server in the substation for synchronizing the non-PTP devices. And then you need to have a master clock with PTP for synchronizing the rest of devices. They are separate messages and they are completely compatible.
Okay, then we have the next question. If you have several PRP and HSR networks, how many GPS units do you need to install? And where do you have to install those GPS grandmaster clocks?
Normally when you're defining a PRP network, you are using two GPS receivers or connected to two grandmasters. It's a matter of redundancy. The two networks are completely separated, and all the equipment, all the devices are connected with to LAN A and LAN B. So you should have a time reference in the two networks. Just in case you lose one of them, you need to have the PTP or the GPS receiver in the second one. So with PRP, normally you have two PTP receivers, and with an HSR configuration, only with one, you should be able to receive the supervision frame from the second link, from the second path in case of link failure.
Okay, perfect. Thank you. So the next one is somebody wants to use virtualization with different virtual machines. And can the virtual machines also access the PRP network? I think I will take this one. So for the virtual machines, it's like with a standard Ethernet interface. So multiple virtual machines can use the same Ethernet interface and connect to the PRP network. The idea behind is that to the outside, the PRP card has two ports to connect to LAN A and LAN B, and to the inside, it is just one standard Ethernet port. So all the processing and acceptance and discarding of the frames is happening within the card. So let's go to the next one. How many red box units do you need to connect several HSR networks with one PRP network, PRP-A and PRP-B?
Normally, you use two devices in a topology where you have to interconnect HSR network with PRP network. Those devices, those red boxes, have to support a specific mechanism, which is or a specific mode, because there are some modes defined in the standard. So it's a mode known as HSR PRP. So you connect the two red boxes inside the ring, and you connect one red box to LAN A and one red box to LAN B. This is the way to perform redundancy and interconnection between HSR and PRP. With two red boxes in one ring, also it's important to have two red boxes, because in case you have one that fails, you have the second one to do the redundancy. If you had only one connected to the two LANs, you will have one single point of failure, which is not something that can be implemented in a redundant network.
Okay, thank you. So the next one is, how many PRP cards can be used within one substation server? I take this one as well. So in one server, we can install 4 HSR PRP cards. So we have 4 PCIe slots. So it's easy that we install them or factory install them here in our factory in Germany, and ship the device to you. In case you are using one card at the beginning, you can also afterwards just purchase the card and install it afterwards. Okay, the next one. as a server can configure some logic to use for tripping and control system? If yes, can we utilize it as defense scheme protection system? In general, yes. So for this application, you probably need to pre-process the sample value streams, and then having some software analyzing and doing tripping and control. We are not doing that kind of software, so you need to look for it. Alicia, I guess you're also not doing tripping and control application within the FPGA, no, but just pre-processing of the sample value streams. So in this case, the software vendor needs to offer this. Yeah. Okay, the next one. Why using HSR or PRP when we already have existing redundancy protocols there?
Oh, I will answer it. Yes, the main benefit of HSR and PRP and the reason why they are being adopted in the electric sector is that they are known as zero packet loss or zero recovery time. With an STP-based protocol like RSTP, the shortest time for recovery is around 500 milliseconds. So with this recovery time, you will surely have some packet loss, and you may have loss of sample values and goods messages that might be critical for be compliant with the response time required in the standard of electric sector, where you have to detect the fault and inform about the fault in less than 3 milliseconds. So these times are not compatible with RSTP or STP protocol, and you need to use a protocol that we call seamless redundancy, so with no frame lost in the communication. And this is the main reason why HSR and PRP are being adopted in that type of networks.
Okay. So there's a question, you mentioned in the webinar that there is no configuration needed for HSR. Why is this the case?
Well, in general, there's no configuration needed for both of them. In terms of red box, with PRP, you will need to configure the switches that are inside the networks, the LAN A and LAN B, because it's a layer 2 protocol. So the only thing that you have to do in the red box is enable or disable the redundancy and select the mode that is going to be used. It's completely transparent for the engineers that are implementing the substation. So it's they are protocols that are being extended to other sectors due to the simplicity and effectivity that they have.
Okay, great. Thank you very much. So it looks like that we don't have any more questions. If you want to ask another question, please take the chance now, or we have to finish this now.
I think we have in the chat part of the Zoom tool. I think there are 2 more questions. I think.
Oh yeah, we have it in the chat. Sorry, yeah. Okay, let me have them. Who is intended user of the Relyum sample value PCIe? Utility end users or manufacturers?
Based on our experience, both yours and mine, we see that at this moment there are projects that are being carried out between both utilities and OEMs. This is my experience because this is something quite new. So normally there are utilities pushing R&D projects for analyzing the benefits of those type of solutions, centralized protection, and of course the manufacturers, the big technology providers for this industry that are working on the development of new solutions, like for example central protections. This is my experience. I don't know if just you want to add something different or.
Well, I totally agree. On one hand, we are working with vendors on those concepts and solutions. On the other hand, the utilities are always integrated in this because without the utilities, vendors cannot do that, and without the vendors, the utilities cannot do it on their own, or not more than an R&D project. Okay, perfect. Let's come to the next one. What are the use cases for Velotech Rack Substation Server? How can it help our existing digital substations that use process and station bus? Is this a possible replacement for SCADA RTUs, e.g. Orion Elix RTU? Yes. So you can use it in the station bus, for example. A typical application is that you are running a substation gateway and the HMI on it as two virtual machines. And if you want, you can also add a firewall on it or engineering workstation. So based on the demand of the single virtual machine, you can run 4 to 5 or maybe 6 different applications on one server. This is on the station bus where you don't have hard real-time requirements. If it goes into the hard real-time requirements on the process bus, it can run protection and control algorithms, probably in combination with a real-time operating system like VxWorks, or a real-time operating hypervisor like the Helix platform from Wind River, and of course the pre-processing of the sampled values with the card from Relyum. Okay, one more. Is it possible to use one physical switch in the PRP network, just dividing it on 2 virtual for A and B networks by using VLAN?
No, in the basics of PRP is to have completely separated networks. When I was talking about HSR, I said that redundancy has to avoid a single point of failure. If you have only one switch and you have any problem in one switch, you will lose both with this configuration LAN A and LAN B. So all the PRP networks rely on 2 completely separated physical devices, 2 networks completely separated, and the same networks, the same topology for LAN A and LAN B.
Okay, then we have another question. Does a NIC have an optical interface? You want to take that, or should I do it? I'll do it. So the NIC for HSR and PRP are SFPs, so you have the possibility to have copper inserted or fiber, so you are flexible in these different combinations and can use it for any wavelengths of the fiber network, or any copper that is required. So it also supports 10, 100 and 1000 Mbits. And especially for legacy applications, 100 Mbits is quite important. Many fiber cards on the market are not able to do that. So in those cases, this card can also work just as a fiber card for 100 Mbits. Okay, I think.
One more, Josh, I think in the chat also.
Okay, one more. Does a Velotech server have built-in systems that support IEC 61850 MMS? No. So the server just is a platform that runs applications, so you can run multiple applications on it, and there could be an application from a vendor like Siemens, GE, Hitachi ABB or ABB, or also smaller vendors, or just software vendors like Copper Data and the Xenon SCADA. So you can run those applications, and they usually support MMS. I think this was the last one.
Yes.
Okay, great. So thank you very much for joining, and it was great that so many people were here. Yeah, see you soon. If you have any additional questions, please feel free to get in contact by email to both of us, and or get in contact with our sales. So we'll help you. Thanks a lot.
Thank you.
Bye.
Bye.